excitement and relief as the Large Hadron Collider subsystems whir back into action, setting a new world record.
Scientists around the world were left stunned when the Large Hadron Collider at CERN, humanity's most powerful particle accelerator, produced a collision unlike anything ever seen.
Most powerful particle accelerator, the Large Hadron Collider. Scientists around the globe are hoping that the upgraded machine, which is massive, will be able to detect new particles and start a physics revolution that could forever change our understanding of the whole universe.
Two mysterious particles, previously unrecorded in any experiment, interacted in a way that defied known laws of physics. The resulting data has sent shockwaves through the scientific community, hinting at phenomena so extraordinary that researchers themselves are cautioning about the limits of human experimentation. What they have found has left the world in shock. The silence in the detectors. In late 2023, deep beneath the rolling hills along the French-Swiss border, the Large Hadron Collider thrummed with its usual, almost hypnotic precision. The cavernous underground tunnels of CERN echoed with the low mechanical drone of superconducting magnets, each one colossal and precisely cooled to near absolute zero by a labyrinth of cryogenic systems. The hiss of liquid helium circulated tirelessly, maintaining temperatures colder than the depths of interstellar space, while particle beams raced around the 27-kilometer ring at velocities approaching the speed of light. Outside, the world went about its day, blissfully unaware that deep below, humanity was probing the very fabric of existence itself. It was a routine day, or so it seemed. Then, for a fleeting 27 microseconds, a span so brief that it would be missed even by the fastest human reflex, the detectors fell utterly silent. The instruments, engineered to capture a symphony of subatomic chaos with mind-boggling precision, recorded nothing. No collisions, no tracks, no energy signatures. A perfect void, as if the universe had pressed pause. Yet, in that imperceptible silence, something extraordinary unfolded, something that would send ripples through the corridors of theoretical physics. Two remnants of prior collisions, particles that should have long since decayed or scattered into insignificance, met again. But this was no ordinary interaction. The collision produced energy signatures that violated every expectation, patterns that defied the standard model, asymmetries that should not have existed. It was as if the laws governing the subatomic world had been momentarily rewritten, hinting at a particle that, by all prior knowledge, should simply not exist. In the control rooms, the reaction was electric. Experienced scientists, accustomed to the strange and exotic behavior of high-energy collisions, stared at their screens in disbelief. Simulations were rerun, calibrations double-checked, and cross-checks against every possible error source conducted. Every hypothesis that could explain the anomaly as a technical fault or statistical fluke was exhausted. Even the most confident physicists were forced to confront an unnerving question. Had they witnessed a momentary violation of reality itself? The silence of those 27 microseconds was as profound as it was fleeting. Its implications cascaded almost instantly through CERN's internal communications. Publication channels were halted. Drafts were suspended. Experiments were recalibrated. Reassurances to the outside world were delayed, pending months of rigorous verification. Yet, in whispered conversations and private logs, the acknowledgement was clear. Something unprecedented had occurred. The universe had, for the first time in human experience, presented a phenomenon that could not be neatly categorized, quantified, or predicted. A direct challenge to the limits of human understanding and the very framework upon which modern physics is built. In that brief heartbeat of silence, the familiar order of particles and forces seemed to wobble. The detectors had not merely failed, they had recorded the possibility of something beyond everything scientists thought they knew. And though the world would remain unaware for some time, deep in the tunnels beneath Europe, humanity had taken a step into truly uncharted territory. A fleeting glimpse of reality pushing back against our attempts to measure, control, and comprehend it. Echoes of past anomalies. The 2023 anomaly did not appear in isolation. For those immersed in CERN's decades of experimentation, it carried echoes of earlier events that had both puzzled and eluded the scientific community. In 2018, the CMS detector had recorded a curious signal, a 28 giga-electron-volt muon pair forming with properties that defied classification. Though subtle, it was unmistakable, a fingerprint in the data that did not match any known particle or decay process. The scientific community buzzed with intrigue. Drafts of papers were circulated, theoretical models were proposed and debated in hushed corridors, and late-night discussions spanned from the practical to the philosophical. But then, almost as abruptly as it had appeared, the signal vanished upon reanalysis. Officially, it was labeled a statistical fluctuation, a random quirk of data that carried no lasting significance. To outsiders, the case was closed. To insiders, it left a lingering question mark, a quiet hint that the standard model might not tell the whole story. Fast forward to 2023 during an oxygen-lead hybrid collision run, and history seemed to repeat itself, but in a way that could not be ignored. The detectors registered a strikingly similar energy signature, occurring under conditions entirely different from those in 2018. Statistically, the likelihood of such a coincidence appearing twice across two fundamentally distinct experiments was vanishingly small, essentially pushing the boundaries of probability itself. Within CERN's internal logs, this repetition set off alarm bells. Researchers began cross-referencing archived data, meticulously verifying instrumentation, and re-examining simulations that once had seemed conclusive. The emerging pattern hinted at something far more profound than mere statistical error, a subtle, persistent anomaly that might point to a hidden particle, a new interaction, or even a phenomenon that challenges the very rules governing matter. What had once been dismissed as noise was now gaining the weight of suspicion. If the 28 giga-electron-volt signature was real, and if it had recurred under different circumstances, the 2023 anomaly could not be ignored. CERN was confronted with a mystery that straddled the boundary between discovery and the unknown, a puzzle that forced even the most cautious scientists to confront the extraordinary possibility that the universe had just revealed something fundamentally new and deeply unsettling. Breaking the rules of matter. By 2025, the LHC had moved into a new era of experimentation. Heavy ion hybrid runs, where different types of atomic nuclei, some fully stripped of electrons, others partially ionized, were accelerated and smashed together at nearly the speed of light. What emerged from these collisions was nothing short of breathtaking. Within the cavernous detectors, hundreds of particles flashed into existence every microsecond, forming a dazzling, chaotic storm of subatomic debris. Amid this maelstrom, something extraordinary occurred. Two particles, so rare that they were previously unregistered in any beamline manifest, interacted. The collision was accidental, unplanned, and instantaneous. Yet it may have created a phenomenon that defied one of the most fundamental laws of physics: baryon number conservation. This law, a cornerstone of particle physics, dictates that the total number of baryons, protons, and neutrons remains constant. It is what ensures that matter, from atoms to planets, cannot simply vanish. For a fleeting instant, however, the data suggested that matter might have ceased to exist, converting into a state that was not simply energy, nor anything the standard model could describe. Inside CERN, discussions among senior engineers and physicists became tense. One off-record engineer confided that if this reading were confirmed, it would upend the very foundations of physics. The implications were staggering. Matter, the building block of the universe, might be far more fragile than anyone had dared to imagine. In practical terms, this wasn't about science fiction. It wasn't a distant cosmic event or a thought experiment. This was happening in a controlled laboratory, within the confines of human technology, and it exposed a reality that could force physicists to rethink the permanence of matter itself. Questions that once seemed purely philosophical about why anything exists at all were now grounded in experimental evidence. If a particle could vanish in this way under controlled conditions, the stability of the universe might be less absolute than previously assumed, and the door to phenomena once relegated to theoretical speculation had swung open wide. Quantum vacuum on the edge. The mystery deepened when researchers began contemplating the false vacuum hypothesis, a concept long discussed in theoretical physics. According to this idea, our universe exists not in the most stable possible state, but in a temporary configuration that appears stable because we have never observed anything else. In other words, reality as we know it could be a bubble of apparent stability, teetering on the edge of a more profound, lower energy state. CERN's hybrid collisions are unlike anything previously achieved. By concentrating extraordinary energies in infinitesimally small volumes, these experiments probe conditions that may exist nowhere else in the observable universe. Theoretically, a collision of sufficient intensity could nudge the quantum vacuum, potentially initiating a cascade that transforms the vacuum into a new, lower energy state. Such a collapse would propagate outward at the speed of light, rewriting the fundamental laws of physics and creating a region of space-time where atoms, molecules, and matter as we know it could no longer exist. Though speculative, the implications are chilling. Every heavy ion collision, every unexpected anomaly, brings researchers face to face with the limits of human control over reality itself. Theoretical models can predict outcomes with extraordinary precision, yet here at the frontier of high-energy physics, the boundaries of certainty blur. Experiments that create conditions never before observed in nature raise an unsettling question. Are we, in our pursuit of knowledge, inadvertently pressing against the hidden scaffolding of reality, potentially exposing the universe to risks we do not yet comprehend? In that sense, CERN's breakthroughs are not merely about discovering new particles, they are a direct confrontation with the stability of existence itself, a reminder that in probing the smallest building blocks of matter, humanity may be brushing against forces that govern the very fabric of the cosmos. Time breakers and CP violation. The concept of time as a constant linear flow is one of the most deeply ingrained assumptions in physics and philosophy alike. But inside the subterranean tunnels of CERN, this notion began to wobble. Researchers working with the LCHB detector, which specializes in studying the behavior of B mesons, began to notice something profoundly unsettling. Certain decay processes were occurring differently depending on the direction of time. In other words, time itself might not be symmetric at the quantum level. This is the phenomenon known as charge parity (CP) violation, first observed in the 1960s, which shows that certain subatomic processes do not mirror perfectly when reversed. What makes the recent data extraordinary is that between 2022 and 2024, new, unexplained patterns of CP violation emerged. These anomalies could not be accounted for by any existing model. Instead of behaving as expected, some particles decayed in a way that suggested the universe has a preferred direction for time, a subtle but profound arrow embedded into the fabric of reality itself. The implications are staggering. If the flow of time is locally asymmetric at the quantum level, then causality, the relationship between cause and effect, is not as absolute as we've always assumed. In practical terms, this means that under certain extreme conditions, particle interactions could momentarily distort the flow of time within the detectors themselves. Imagine a region, smaller than a human cell, where events unfold in a sequence that does not align with the standard forward march of time. While imperceptible on a human scale, such distortions would redefine our understanding of how reality operates at its most fundamental level. Inside CERN, discussions about these anomalies have been careful and measured, yet one cannot ignore the philosophical implications. Scientists are beginning to ask questions that edge toward the metaphysical. If time itself can favor a direction, then how stable is the universe we experience? Could controlled experiments inadvertently influence these local distortions, however briefly, altering the flow of events in ways we do not yet comprehend? These questions move particle physics from a purely empirical discipline into the domain of cosmic philosophy, raising the unsettling possibility that observing the universe might in some way shape it. Hidden dimensions and the portal experiments. While the collisions in the main LHC ring capture headlines and public imagination, some of the most ambitious and enigmatic experiments at CERN occur quietly, in parallel, outside the central detectors. Programs like FACER, MODAL, and Methuselah are purpose-built to explore phenomena that standard setups cannot capture, probing the boundaries of what is known and what is conceivable. Phaser, located hundreds of meters downstream from the main detectors, watches for particles that travel through enormous distances of matter, essentially passing right through the Earth, without leaving a trace in conventional instruments. Meanwhile, Modal has been dedicated to capturing magnetic monopoles and highly exotic particles, elusive phenomena that, if confirmed, could upend decades of theoretical assumptions. Above ground, the massive Methuselah detector sits silently, scanning for long-lived particles that traverse hundreds of meters of rock before finally decaying. Each of these experiments is a window into the hidden, subtle dynamics that the LHC's central detectors might miss entirely. The focus of these specialized detectors is not merely fringe physics. They are designed to search for dark photons, axion-like particles, and other hidden sector messengers, theoretical entities that could bridge our universe to dimensions we cannot directly perceive. These hidden sector particles, if detected, might reveal layers of reality that exist alongside our own, intersecting with our familiar world in ways both subtle and profound. What makes these experiments particularly remarkable is how coordinated anomalies can appear across multiple detectors. When energy spikes, particle tracks, or decays synchronize in unusual ways between Phaser, Modal, and Methuselah, researchers are forced to consider possibilities that go beyond conventional physics. Some insiders speculate that such coincidences might even represent brief, fleeting intersections with realities beyond our perception, ephemeral windows into phenomena that challenge the very boundaries between what exists and what can be measured. These hidden experiments transform CERN from a site of particle collisions into something far more profound, a laboratory not just for understanding the known universe, but for detecting the unseen, probing questions about dark matter, hidden dimensions, and the fundamental nature of existence itself. The anomalies recorded in these detectors hint at a reality that is far more complex and layered than our senses, or even our most advanced instruments, can fully capture. Lessons from past shocks. CERN's history is a testament to human ingenuity, and to the razor-thin margin between controlled experimentation and chaos. In 2008, during the commissioning phase of the Large Hadron Collider, a catastrophic magnet quench sent ripples through the accelerator's complex network of superconducting magnets. Energy levels far beyond the normal operating range surged through the system, causing multiple superconducting magnets to fail almost simultaneously and threatening the structural integrity of the collider itself. Repairs required months of painstaking work, billions in funding, and a renewed respect for the sheer power harnessed beneath the French-Swiss border. Yet the story does not end there. Decades of experiments have taught physicists that extreme electromagnetic fields can subtly influence the quantum vacuum, the underlying fabric of empty space from which all particles and forces emerge. Under these extraordinary conditions, virtual particles flicker in and out of existence, and the usual behavior of matter can become temporarily altered. In practical terms, this means that even within a controlled laboratory environment, the universe has a way of reminding us that it is not a machine to be perfectly commanded. In 2024, several detectors once again recorded anomalous fluxes, exceeding predicted safety limits by nearly 18%. These surges were brief, lasting only seconds, but they coincided with unexpected detector failures. Official statements attributed the events to routine technical fluctuations, minor cooling issues, or standard calibration errors. However, insiders familiar with the operations whispered of something more profound. These readings, they suggested, were subtle reminders of the delicate boundary between experimental exploration and the forces that govern reality itself. Even in the controlled corridors of CERN, the universe was asserting that pushing the limits of particle physics was not without consequences. Physicists often speak in probabilities and error margins, but the 2024 anomalies highlighted a deeper truth. Our experiments may be approaching thresholds where nature's laws, as we understand them, are no longer predictable. Every high-energy collision carries with it the potential to reveal not just new particles, but glimpses into the fundamental stability of matter, energy, and the vacuum itself. High luminosity, LHC, the next frontier. The next leap forward comes with the High Luminosity Large Hadron Collider, HLLHC, scheduled to begin operations in 2029. This upgrade is not merely incremental, it represents a quantum leap in experimental capability. By increasing the collision rate tenfold, the HLLHC will allow scientists to observe ultra-rare events that previously might have occurred only once in a trillion collisions, making the invisible visible and turning theoretical possibilities into experimental realities.